Okay, so let's continue with this key rental problem. So it's just a key rental part 2. Now, there is a proposition or theorem, whichever you prefer, that effectively says that this algorithm AB is an optimal one in terms of competitive ratio amongst all those deterministic online algorithms. So it says that if A is a deterministic online algorithm, for the key rental problem, then its competitive ratio, so competitive ratio is at least 2 minus 1 over b. So basically it says that since AB has exactly this competitive ratio, so this is an algorithm having the smallest possible competitive ratio, so that's why we call this AB is an optimal algorithm. Optimal. Well, more precisely, it's optimal among the deterministic algorithms. Now, there is a possibility that you haven't ever heard this word, deterministic. So I just try to explain it. Deterministic means same input is always resulting in the same output. So same input, same output. So for example, there is no random involved when you produce the output. And also, so if the algorithm on some input produces some output, so let's call this is a vector, okay, this is another vector, then if we just continue this sigma 1, so if it's a deterministic algorithm and it's online, then for the first input it produces an output value, on the second input produces a value, and so on. So if you just start your input with the very same sequence and then continue it with something, and then this guy always starts by tau 1. So it's basically just the same input, same output, and this is just the same prefix of the input, then is the same, starts by tau 1. Of course it will output something for this part of the input as well, but the prefix is the same. So what we will show is that if A is any algorithm, then its competitive ratio is at least this one. Now, in order to prove those things, so it's called a lower bound for competitive ratio, it's enough to construct one wrong input, one bad input for this algorithm A. It's enough to construct one bad input for each A. Bad means that if you run the algorithm on this sigma and compute the cost of the output and you divide it by the optimal cost, then it's already larger than 2 minus 1 over b. Usually that's enough, so that's always enough, and usually we do this. So we just give bad enough input sigma for each A that moves over this 2 minus 1 over b. So let's try to construct a bad input for an algorithm. So for this, and let A be some algorithm. So it's deterministic algorithm. And let's consider say the following inputs. The inputs 1, 1, 1. So there's 2 snowy days. 1, 1, 1. Yeah, so that's just 3 consecutive snowy days. 1, 1, 1, 1. 4 of them, and so on. For how long? So it's 2b those days, blah blah blah. 1. Oh well, we can set this to b minus 1. Okay, so this is just a sequence of inputs, and I say that the algorithm will behave badly on at least one of these. So the algorithm behaves badly on at least one of these. So of course any deterministic algorithm will just it either rents on the first day or buys, and if it buys then it's fine. Otherwise, if it rents, then it will choose or decide what to do on the second day. It's also either renting or buying, and so on and so on. So there are many possibilities. So first case, it can happen that the algorithm keeps renting. The algorithm A just keeps renting for 2b minus 1 days. So it just keeps renting for 2b minus 1 days. So basically it means that for this particular sequence of input, this output sequences R, this output sequences R, this output sequences R, but of course whatever the output sequence is for this length 3 input, this part is the same as this part because the algorithm is deterministic. So since the input is the prefix of the other input, the output will be also a prefix of the other output, right? So it's fine. So if A keeps renting for 2b minus 1 days, then for the last one, the optimal cost is B, because so 2b minus 1 is the number of ones, and the optimum is always the minimum of the number of ones in the input, and B, and since this n is 2b minus 1, it's, well, at least as large as B. So the optimum is B, while if you just keep renting for 2b minus 1 days, the algorithm's cost is 2b minus 1. So the ratio in that case is just 2b minus 1 divided by B, which magically happens to be 2 minus 1 over B. Yeah, right. So for this case, if the algorithm keeps renting for this large amount of days, well, then its competitive ratio is at least 2 minus 1 over B. Otherwise, there is a first day on which it will buy something. Otherwise, so K is somewhere between 2b minus 1 and 1. So let this K be the first day, be the day when it buys the skis. Be the first day on which A buys the skis. So this means that, for example, if K would be 4, like, then it means that for 1, 1, 1, 1, the output is just rent, rent, rent and buy, because this is the 4th day. So this is the first day on which A buys the skis, and of course during the previous days it's just renting, because there is no, but it's not buying, so it should be renting. Now this means that the algorithm's cost is K minus 1 for renting plus B. So this is the renting cost, right? So it's K minus 1 days and plus this guy, the cost of the skis. And then the optimum is always the minimum of K, the number of the days, and B. Now there are two cases, because the minimum can be either K or B. So it says that if K is at most B, and the second case is when K is larger than B. So if K is at most B, then the optimum is K. And if K is larger than B, then the optimum is B, right? And then, if the optimum is K, then the algorithm's cost divided by the optimum is just K minus 1 plus B over K. and I should make this larger than something because I want to prove a lower bound, but since here is a b and b is larger than k, so it's just k minus 1 plus k over k, which is, well, this is 2, that's for sure. Let's just change this a little bit. I could finish this, but if k is strictly larger than b, then we still have two cases. So, and the other case will be when k is at least as large as b. Now the thing is, here b is at most. In that case, k plus 1 is an upper bound, lower bound for b, right? Since both of these guys are integers, then if k is smaller than b, then k plus 1 is either smaller or equal to b. And this is a somewhat more usable stuff because it makes k minus 1 plus k plus 1 here. So k plus 1 is used as lower bound for this guy, divided by k, and now these two guys, the plus 1 and the minus 1 magical cancel each other out, and then we just have 2. So I wanted to make sure that k is not occurring in the end result because it should be independent of the input. But here in this case, the competitive ratio of the algorithm is proved to be at least 2, which is of course at least as large as 2 minus 1 over b, so it's fine. Now for the other case, there will be difference. So the algorithm divided by the optimum, remember this is the ratio we are calculating all the time during the whole semester. So it's again k minus 1 plus b, but the optimum in this case is just b, right? B. And again, if I want to lower bound this guy and I know that k is at least as large as b, then I can change this k into a b divided by b, and now I have a ratio. This guy here is simply 2 and that guy over there is minus 1 over b. So in both cases the ratio for this particular input is at least 2 minus 1 over b. Yeah, that's the important part, which proves our claim that 2 minus 1 over b is a lower bound for any deterministic algorithm's competitive ratio. Now I will make another video for another problem, so it's enough for the ski rental problem. We just proved that the algorithm which buys on the birthday, snowy day, and rents during the previous snowy days is optimal in the sense that it has the best possible competitive ratio amongst the deterministic algorithms. However, we will prove that if we also allow randomization, then there are better algorithms for this problem. But next time we will move on with the so-called paging problem, which you might be familiar with from your previous studies on operating systems. Till then, bye bye.